All right, this is the second part of the calculus lesson, the first derivative test, lesson 2, which I said high school. Calculus is a college course. Some high schools offer it, so sorry about that. Okay, so we know how to find the critical points of a function. We know how to determine where a function is increasing or decreasing by analyzing the sign of the first derivative. Now let's go back to those critical points, those C values, where the derivative is either undefined or where the derivative is equal to 0. There are a few things that we need to discuss about those critical points. If at a critical point on your function, and assuming that your function is continuous on an open interval, we're going to call that open interval I. If it's continuous, there's no breaks or gaps. You can trace the function without lifting your pencil. That's the layman's definition of continuous function. If it's also differentiable on that open interval, that means that the derivative is defined everywhere. There are no undefined values. Then those critical numbers that you find, basically where the derivative is equal to 0, can be a very special point. You know that where the derivative is 0 is where the graph levels off. If the derivative, the slope of the tangent line, changes from negative to positive, so negative on the left, positive on the right, and here's your critical point where the slope of the tangent line is 0. If the derivative changes from negative to positive, then you know that that critical point can be classified as a relative minimum. That means within its interval, relatively speaking, it is the lowest point in that interval. It's called a relative minimum. It's not necessarily the absolute minimum point on the graph, because it's possible that later on, depending on what kind of function you have, the function could make another turn and go lower than that point. But in that interval, we call it a relative minimum. That is the lowest point. So if the derivative changes from negative to positive, we classify it, that critical point, as a relative minimum. If the derivative changes from positive to negative, it's positive on the left side of your critical point. Remember, here's your critical point where the derivative is 0. And then the slope of the tangent is negative. So it's positive on the left, negative on the right. Then we say that that is a relative maximum. In that particular, on that interval, in that region, that is a relative maximum. It's a maximum in that particular area, so it's a relative maximum. That's a better way to say it. If the derivative doesn't change, it's either positive on both sides or negative on both sides. For example, let me see if you can see this. Let me prop this just a little bit more. There we go. So let's say we have a critical point here, because that's where the tangent line is 0. If the slope of the tangent lines on the left and on the right don't change, they're either positive on both sides, or let's say they're negative on both sides, these would have negative derivatives, negative tangent lines, then it's neither a relative maximum or a relative minimum. Okay? So that's called the first derivative test. If you're trying to determine if your critical point is a relative max or a relative min, you examine to the left and to the right. So let's go back to our problem that we've looked at a minute ago. If you remember, the original function was f of x equals x cubed minus 3/2 x squared. We took the derivative of that and we set it equal to 0, and we got our critical points. I'm not going to do all that. Sorry about that. I'm just going to recap here. That was our original function. Our derivative was 3x squared minus 3x. We got two critical points, x equal 1 and x equals 0. And if you remember on our sign analysis, I'm not going to repeat the sign analysis, but this is what was going on. This was our sign analysis that we did last time. You can review back lesson 1 if you need to. But let's just talk about this. So this is our sign analysis of the derivative. At this critical point, this is like our C value. To the left, it is increasing and then it's decreasing. So using that first derivative test that we just talked about, if it's increasing on the left and then decreasing on the right, we know that we have a relative maximum at this particular critical point, which is x equal 0. Now, because we are very interested in the entire point and the y value is what makes it maximum or minimum. We're going to figure out what that y value is in a minute. We'll talk about that. But let's look at the other critical point. This other critical point at x equal 1 was decreasing to the left and then increasing to the right. So it decreased and then increased. That makes that critical point a relative minimum. So we have a relative minimum at x equal to 1. Now to find the y value, you know that y is the same thing as f of x. So basically you can plug your x value into the original function, not the derivative. Go back to the original function to get the y value that is associated with your x value. So I'm going to go back to the original function. I'm going to plug in 0 in for x. 0 cubed minus 3/2 times 0 squared is 0. So the point 0, 0 is a relative max. A relative minimum is at x equal 1. To get its y value, I go back to the original function and I'm going to plug in 1. This time I'll write it out a little bit. 1 cubed is 1 minus 1 squared, doing the order of operations correctly, do the power first. 1 squared is 1 times 3/2 is 3/2, and so it's 1 minus 3/2, which is negative 1/2. So the point 1 comma negative 1/2 is a relative min. So putting this together on a graph, I'm not going to graph everything. I could go and try to find x-intercepts and y-intercepts, which is really easy. To get an x-intercept, you set y equals 0. To get a y-intercept, you get x equals 0. But haha, look at there. I already have the x-intercept and the y-intercept. It just happened to come out in the wash when I was doing my first derivative test. But you could get additional points. But what I know, just knowing these 2 points and the increasing or decreasing intervals, I can make a sketch, not an exact graph, but a sketch of my original function, which was x cubed minus 3/2 x squared. All right, 0, 0, there's that point. The relative minimum is at x equal 1, y equal negative 1/2, which is about right there. All right, going back to the information that we had before, I know that from negative infinity to 0, my graph was increasing. One thing I don't know from the first derivative test right now, I don't know if my graph is going to increase like this or increase like this. Both of these graphs are considered increasing because from left to right, they're both going up. But you'll notice they have a different bend. We're going to talk about concavity at another point, possibly. This would be considered concave up. This would be considered concave down. And because I know what x cubed functions look like, I'm going to go ahead and use my prior knowledge. I'm going to graph it with the correct bend to it. But with what we've talked about in the first derivative test, we have not talked about concavity yet. So technically, if you drew it that other way, we hadn't talked about that yet. So I wouldn't count that against you yet. All right, so I know that the graph is increasing. This is where it levels off. That's a relative maximum. So in that general vicinity, that's going to be the highest point in that area. And then the graph it decreased from 0 to 1. The graph goes down between 0 and 1 until it reaches a relative minimum at 1, negative 1/2. And here's negative 1/2 right here, just estimating. And then if you remember from your sign analysis, it was positive, increasing from 1 to infinity. So that means the graph is going to go up. And I could easily find out where that other x-intercept is, because it is going to have to cross the x-axis again to be able to be an increasing graph after that. And I could easily find that because that's an Algebra 2 concept. You just take your original function, set it equal to 0 and solve it, and that'll tell you what that point is. For now, I'm just going to leave it off of there, but I just wanted to show you the relative max, the relative min, and how the increasing and decreasing information that we got from the first derivative test was helpful here. Okay, that's lesson 2, short.